Hello students, welcome to the second video on the module 5 of our subject electronic devices. So in this video we will be discussing about what is meant by diffusion and ion implantation process. So in the previous video of this module we have discussed what is meant by thermal oxidation. So thermal oxidation is a process in which we will be having the silicon material converted to silicon dioxide. So what is meant by ion implantation and diffusion process? So this is nothing but doping of impurities. For example, if we have this setup, if this is the source and this is the silicon wafer we have, so silicon wafer is nothing but a pure silicon material, and we have the silicon dioxide material on these two edges and the center is open. Now, when a source is there and due to some process, either due to the applied electric field or due to the concentration gradient, if there is a movement of ion on this surface, so we know that these ions will get penetrated or it will move inside this surface, and hence because of this the only region which is exposed to this ion will be converted to the corresponding layer. That is, if it is a pentavalent impurity, it will be converted as it will be changed to N type, or if it is a trivalent impurity ions, then this will be converted to the P-type region. So what is this oxides? So oxides are nothing but the insulating layer which will prevent the diffusion or the ion implantation process. So in this video, we will be discussing in detail about these two processes, that is diffusion and ion implantation. So these are used to introduce the impurities into the silicon dioxide so that we can change the material or we can change the concentration of the carrier type, and also because of that the resistivity of the layers will be changed. So there are two processes, one is called as diffusion and another one is called as ion implantation. So we know that diffusion is nothing but movement of some material or some particle from the surface of lower concentration or higher concentration to lower concentration. So here in this diffusion process, the dopants will move from the surface, that is where it is highly concentrated. So the dopants or the impurities will move from that surface into the silicon material by means of some diffusion mechanisms like substitutional or interstitial. So what is ion implantation? So ion implantation is another doping process. Here the dopants are forcefully added into the silicon in the form of the high energetic ions. So here coming to the diffusion process, so the main important goal is we need a very controlled depth. Depth is nothing but the height to for which the doping will be happening. That is, if I take here, if I want to make it as P plus, the thickness, or I can say the height of this P plus region is called as the junction depth. And also I need a controlled concentration, doping concentration. So controlled doping concentration is nothing but wherever I want my doping to be heavy, there it should be heavy, and all the neighboring regions should not be affected by this. So for me the main goal is there should be controlled junction depth as well as the controlled dopant concentration under the profile. So maximum concentration can be either here or it can be somewhere down. So to accomplish my job, I am going for the doping process. Now, we have two processes, one is diffusion and another one is ion implantation. So diffusion is nothing but a simple process in which there will be concentration gradient movement, but here the main important thing is it is an isotropic dopant profile. Isotropic means that the doping will be happening in all directions, so we cannot control the dopant concentration as well as the junction depth independently. Whereas here in ion implantation, the process is controlled in the sense that I can just control the junction depth, also the region where my doping should be done. So since it is a controlled process, so ion implantation is it is normally advisable for all high precision device manufacturing. So what is diffusion? So as we have discussed, diffusion is movement of charged particles from high concentration to low concentration. So the diffusion of impurities takes place at a temperature in the range of 900 to 1100 degrees Celsius. So this is a simple setup which says how a diffusion process works. It is same as the oxidation process. The only thing is we will be having the impurity for material whatever to be doped here will be here stored here, and then when it is sent or when it is it converted to gaseous state, and when it is passed through this furnace, so we can which is covered by a quartz tube, you can see that silicon wafers will be getting deposited, or there will be change in the property of the silicon wafer based on the doping impurities. So here, normally boron will be used for an p-type impurity, for introducing the p-type impurity. Arsenic and phosphorus are usually used as an n-type dopant. So normally here, in the diffusion process, the doping concentration is large, or it will be more at the surface. And as we go deep inside the substrate, so there will be decrease in the doping concentration in the Gaussian manner. So the diffusion can be taking place in two process, mainly two process. One is called as pre-deposition and the other one is called as dry vena. So pre-deposition is nothing but there will be an uniform or constant doping profile throughout the surface. Whereas here in case of dry vein, the impurity will be deposited, and hence because of that there will be the impurity gradient at the surface of the substrate will be changing with respect to the time. So the diffusion process mainly depends upon the temperature at which the process happens. Also, the type of impurity plays an important role in the diffusion. The diffusion time is nothing but the time which is taken for the process, and the defects in the crystal also plays an important role in the diffusion process. Now, so the crystal structure, the junction depth control, and the doping concentration control are the main important challenges we will be facing here in the diffusion process. The main advantage of the diffusion process is it will not damage because there is no electric field applied here. It is just the concentration gradient. So here no damage to the surface. Also batch fabrication is possible here. So we can do a large amount of diffusion process can happen over a large surface, and it is an isotropic process. Hence your diffusion will be uniform for all the direction, and also it's economically it's good when compared to ion implantation. But the disadvantage is this: the doping concentration as well as the doping depth is not controllable, and also we cannot carry out this process at room temperature. To avoid these disadvantages, we go for ion implantation. So, what is ion implantation? It is a contamination free setup where we will be having good control of the depth. The depth can be controlled in terms of micrometers, but the crystal damage is one of the disadvantage of this process. So here we can see the setup where the iron impurities will be accelerated to a very high temperature, and then it will be passed through the mass separator. The mass separator is a place where the recovered gases alone will be left here, passed here. So here this will be again accelerated, drifted, and with high energetic ions will be going and striking on the target chamber. The target chamber is nothing, the place where our wafers are there. So when the ion beams are getting striking the wafer, it gets ionized, or it will be converted to p type or n type based on, or the impurity concentration will be varying based on the process. So that this diagram explain gives a clean picture here. So the ion source, it is separated and then it is accelerated and it comes and falls on this substrate where it is rotatable. So it will be very precise. The process will be precise and it is controlled. So the junction depth as well as the profile concentration can be controlled by means of the ion implantation. So next video we will be discussing about the other process. Thanks.